Hello and welcome to today's session. We're looking at Coulomb's law and we'll look at the similarity between this and Newton's law of gravitation. So following on from our work on gravitational fields. Okay, so we looked at gravitational attraction, so the gravitational force. We looked at Newton's law of gravitation. So F is equal to G M1, M2, or capital M, little m, over R squared, where R squared is a separation, G is the gravitational constant, and M's are the masses of the object. So this was an example of an inverse square law, which always pops up in physics. And we're going to look at this and see how it compares to the electrostatic force, which is Coulomb's law. So that's what we're going to do. So with this, as a recap, how can we find the force? So we need to substitute our values in. If we recall, we're given the values on the formula sheet for the masses. So the mass of a proton is 1.6 times 10 to minus 27, so 1.6 times 10 to minus 27 kilograms, and an electron is 9.11 times 10 to minus 31 kilograms. The gravitational constant is also given on your formula sheet as well. So this is what we do. We'd substitute our values in. And the gravitational constant, which is given to you, which is 6.67 times 10 to the minus 11. So we'd substitute our values in and calculate. So let's do that. 6.6. And the separation, so that's squared. So that's what we do. We put that into a calculator and find the force. We can also compare the values of the gravitational force and then the electrostatic force once we've done it later on, and we'll see how they vary in size. So we put that into our calculator and then work out a value for the force. So if we do that now, there's a gravitational force to two significant figures of 1.1 times 10 to the minus 48 newtons, which is extremely small. So that's the two significant figures. So that's what we did in gravitational fields, and that's a process. In the class sessions, I've said that there's another inverse square law relationship for charges. So gravitational fields dealt with masses, electric fields deal with charges. So the next question to think about is, what would the equation look like for the force between two charges? So what would the formula look like? It's an inverse square law relationship. So we're going to have force F is going to be proportional to 1 over r squared. And we've got two charges. So for gravitational fields, we have the product of two masses. So the electric fields will be two charges. So Q1, Q2 over r squared. And then if we need to turn that into a formula, we'll need to introduce a constant, so a constant of proportionality. So the force are going to be equal to the product of the two charges, Q1, Q2, over the separation of the charges. So that's just following on from what we've seen in gravitational fields to come to a conclusion. If it's an inverse square law relationship and you've got two charges, that would be the force. So for Coulomb's law, if they've got the same charge, it's going to be a repulsive force, and if they've got opposite charges, it's going to be an attractive force. Coulomb's law deals with the magnitude of the force between them. So we deal with the magnitude and the distance as well in terms of a magnitude. So when it comes to rearranging the formula, we need to consider the magnitude so we can find the value of the separation. So we'll look at an example of that dealing with our hydrogen atom. So as I said, the force is equal to Q1, Q2 over R squared, and we write it, the constant can be shown to be equal to 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. That is given to you on your formula sheet. So the permittivity of free space is 8.85 times 10 to the minus 12 farads per meter. And we'll look at that more in capacitance. So when we get onto looking at capacitance. So when you look at your formula sheet, you'll see that the force is written like this. So F is equal to 1 over 4 pi epsilon naught Q1, Q2 over R squared. So that's how it's written on your formula sheet, where epsilon naught is equal to 8.85 times 10 to the minus 12 farads per meter. So that's what we're dealing with. K can be shown to be this, so 9 times 10 to the 9 newtons meter squared per Coulomb squared. And again, we can write that as 1 over 4 pi epsilon naught. So you'll see it on your formula sheet as this, 1 over 4 pi epsilon naught. So we come back to the hydrogen atom. This time we want to calculate the electrostatic force acting between a proton and an electron. So the magnitude of this electrostatic force, and is the force attractive or repulsive? So for both the proton and the electron, we know that the magnitude of the charge is 1.6 times 10 to the minus 19 coulombs. We also know that a proton is positively charged. So when we think about it relatively, the proton is plus 1e, and an electron is negatively charged. So when it comes to this force that's acting between the two, we've got an attractive force. There's going to be an attractive force between these two because they're oppositely charged. So what we need to do now then is calculate the force. So we're finding the magnitude of this. So using our formula, we'll write it as it's stated on your formula sheet. Now we just need to substitute the values in. because they've got the same magnitude of charge, same as squaring 1.6 times 10 to the minus 19. And then the distance is 3 times 10 to the minus 10. Remember to square that value. Then it's just a case of putting that into your calculator and seeing what value you would get. And we'll see that the size of the electrostatic force is greater than the gravitational force between the two. So we get a force to two significant figures of 2.6 times 10 to the minus 9 newtons. So you can see that electrostatic force is much greater than the size of the gravitational force between these two objects, as we looked at in the starter question. So where you looked at the gravitational force, this is much greater. So 2.6 times 10 to the minus 9 newtons, that's the two significant figures. They're oppositely charged, so it's an attractive force. And with this, when you have a question where you need to find the distance and they're oppositely charged, remember to put the magnitude of the charges in there. So put the magnitude of charges in there. So when it comes to finding the distance, you'll be fine on that point instead of getting a math error when you're trying to square root a negative value. Okay. So your task today is to complete the 22.4 summary questions. Remember, that's just to test the understanding of Coulomb's law. So that's the task to complete. You can also have a go at the chapter 22 exam star questions. Those are on Learn Zone. And if you want to do some additional reading around Coulomb's law, so the actual experiment, you can look at Coulomb's torsion balance. So I'll put a link on LearnZone for a YouTube video to the actual experiment. So the experiment where Coulomb came up with this relationship. So that's a good one to look at. So the torsion balance experiment. So that will be on LearnZone. As usual, if you've got any questions, message me via Teams or email and I will get back to you.